You are breathing right now, and you don't even realize it. The universe is slowly dying with every passing second. Not just the stars. Even time itself is running out. And the strange thing is, this process has already begun. And there is no way to stop it. Everything that was born from the Big Bang will one day cease to exist. Not metaphorically. Not in the poetic sense that philosophers mean when they speak of impermanence. In the physical sense. In a mathematically derived, observationally confirmed physical sense. The universe had a beginning 13.8 billion years ago, and the same laws that made that beginning possible have always carried, written silently within them, the guarantee of an ending. The only open question is, how will that ending come? The answer is far more complex than you might think. There is no single scenario. And which of these scenarios is real depends on a single question being measured right now with the most precise instruments in human history. But before we get to that, we need to understand something. We know how a star dies. A star like the sun burns its hydrogen for about 10 billion years, then swells, sheds its outer layers into space, and leaves behind a small, dense, slowly cooling remnant. We have observed this in thousands of different stars. We have seen the different stages of this death across all corners of the universe. The mechanism is understood. The outcome is certain. The death of the universe is not like that, because the fate of the universe depends on a single unknown. And this unknown is one of the greatest mysteries in the history of science. Its name is dark energy. Think about this for a moment. Everything in the observable universe, all the stars, all the planets, all the galaxies, all the atoms, their total contribution is 5%. 5. Of the remaining amount, 27% is dark matter. We can't see it, but we feel its gravitational effects. And the remaining 68%, the vast majority of the universe, is something we don't know what it is. We call it dark energy, not matter. Not light. You can't hold it and examine it. You can't produce it in a laboratory. You can't see it directly. We only know of its existence from this. Space is expanding every second. And this expansion is not slowing down. On the contrary, it is accelerating. A little faster with each passing day. Galaxies are moving apart from one another. And their recession speeds are increasing. Dark energy is behind this acceleration. And here is where the real issue lies. The behavior of dark energy determines the fate of the universe. If it remains constant, the universe will quietly and coldly fade away trillions of years from now. If it grows stronger, one day stars, planets, atoms, even the laws of physics themselves will be torn to shreds. And if it weakens, perhaps everything will one day collapse back and one final Big Bang will occur. 3 different paths, 3 different endings, and we do not yet know which one is real. Tonight, we will examine each of these paths one by one. But first, we need to understand how this story began. Because until 1998, the scientific world believed it already knew how the universe would die. Then 2 research teams simultaneously, completely independently, discovered the same thing. And physics stopped dead in its tracks. To understand why there must be some kind of ending regardless of what dark energy does, you need to understand a principle that sits at the foundation of every physical process ever observed, never once successfully violated in any laboratory, any telescope survey, any particle accelerator in the entire history of science. The second law of thermodynamics states this. The entropy of an isolated system, the quantitative measure of how many different microscopic configurations of the system's components could produce the same macroscopic appearance, can only stay the same or increase over time, cannot decrease. Disorder spreads. Energy disperses from concentrated forms into dilute ones. Organized structures decay toward more probable, more disordered arrangements. This is not a statistical tendency that could be reversed with sufficient cleverness or sufficient time. It is a law in the strongest sense that physics uses the word, a statement about what is possible and what is not, derived from the mathematical structure of physical law and confirmed so thoroughly and so universally that its violation would require overturning essentially the entire theoretical framework of physics assembled over the past 3 centuries. The universe as a whole is an isolated system in the only sense that thermodynamics requires. There is nothing outside it to exchange energy with. No external reservoir of low entropy to draw upon. No external environment into which disorder can be exported. The total entropy of the universe increases continuously with every physical process that occurs anywhere within it, and this increase is accumulating toward a final state that the second law makes inevitable. That final state is the one in which entropy has been maximized, in which energy is distributed as uniformly as possible across all available configurations in all of space, in which no temperature gradient exists anywhere large enough to drive any physical process, in which no concentration of energy at any location is sufficient to do useful work of any kind. This state is called heat death, and every star that burns, every photon that travels across the cosmos, every particle that decays, and every collision between atoms anywhere in the observable universe is contributing to its approach. Not dramatically, not in any way that is visible or measurable on human timescales, but continuously, irreversibly, and without exception. The universe has been moving toward heat death since the very first moment it existed, and it has never paused. Heat death is the ending that follows most directly and with the fewest additional assumptions from the laws of physics as they are currently understood. It is also the ending that requires the most time to arrive. The numbers involved, when you follow the physics from the extinction of the last stars to the cooling of the last white dwarfs to the evaporation of the last black holes through the quantum process that Stephen Hawking theoretically derived in 1974, are so extreme that the universe's current age of 13.8 billion years is not a rounding error but something closer to an infinitesimal fraction of the total duration required. Heat death lies at the end of a timeline measured in numbers that require exponents with more digits than atoms in the observable universe. It is the universe's default ending, the destination that entropy has been navigating toward since the Big Bang. And if dark energy is what the simplest interpretation of the current data says it is, a perfectly constant energy density of the vacuum that neither grows nor diminishes as the universe expands, then heat death is where everything is going, and the journey there is unimaginably long. But dark energy might not be constant. This possibility, which seems at first like a minor technical variation in the standard model of cosmology, turns out to have implications so enormous and so violent that exploring them changes the entire picture of the universe's future. If dark energy is a dynamic field rather than a fixed property of the vacuum, its strength can vary over time. And if that strength is slowly increasing rather than holding steady, the accelerating expansion of space does not merely continue at its current pace but compounds, growing more powerful with every passing moment, until the force driving space apart overcomes not just the gravity holding galaxy clusters together but every other force in nature, one by one, in a cascade of cosmic dismantlement called the Big Rip that tears apart every structure in the universe from the largest scale to the smallest in a sequence that physics can describe with remarkable precision. The Big Rip does not arrive in billions of trillions of years. Depending on the precise value of the parameter describing how dark energy's strength changes with expansion, it could arrive in as few as 20 to 50 billion years. Not an eternity, a finite span of cosmic time that, in proportion to the universe's current age, is not dramatically larger than the time that has already passed since the Big Bang. And then there is the possibility that sits in a different category from all the others, not because of its timescale or its violence, but because of the specific nature of what it would mean for the reality you are inhabiting right now. Vacuum decay. The possibility that the vacuum of space, the ground state of all physical fields from which all particles and all forces emerge, is not in its true lowest energy state but is instead trapped in a configuration that appears stable but is in fact metastable, maintained only by a quantum energy barrier that prevents a spontaneous transition to the true ground state. The possibility that somewhere in the universe, at any moment, a quantum fluctuation could push a small region of space over that barrier and into the true vacuum, initiating a bubble of completely different physics that expands outward at the speed of light, converting everything it touches into a universe governed by different laws, with different particles, different forces, and no possibility of survival for any structure that existed in the false vacuum before the bubble arrived. The possibility that this process could begin anywhere, at any time, without any warning that any physical mechanism could provide before the bubble's expanding boundary reached you, because nothing travels faster than the boundary itself. Current measurements of the Higgs boson, the particle whose field is responsible for giving mass to all other fundamental particles and whose properties determine the stability of the vacuum, place the universe in a region of parameter space that physicists describe as metastable. Not comfortably stable, not immediately unstable, metastable, balanced on a knife edge between the two, in a configuration that could be absolutely stable if physics beyond the current standard model provides additional stabilizing contributions, or could be genuinely unstable on a timescale that is either longer than the current age of the universe by an enormous factor or potentially comparable to it, depending on exactly where on the stability boundary the true parameters of the Higgs potential fall. This uncertainty is not a gap waiting to be filled by a slightly better measurement. It is a reflection of genuine ignorance about whether the ground state of the universe is what it appears to be. These scenarios together, heat death, the Big Rip, and vacuum decay, represent the three most physically motivated, most directly connected to current observational data, and most consequential possibilities for the universe's ultimate fate. But they are not the only ones. The Big Crunch, in which dark energy weakens over time and gravity eventually reverses the expansion and collapses everything back into a final singularity, remains physically possible even if current measurements do not favor it. Cyclic cosmologies in which such a collapse seeds a new Big Bang represent an entire class of theoretical frameworks with serious physical advocates. Most prominently the conformal cyclic cosmology developed by Roger Penrose, which proposes that the heat death of one universe serves as the Big Bang of the next in an endless succession of cosmic eons with no ultimate beginning or end. Proton decay, the instability of ordinary matter itself on timescales far shorter than the heat death but far longer than any human intuition about stability, would dissolve every atom in the universe independently of any other consideration. And at the furthest extremes of physics and mathematics, the concepts of Boltzmann brains and Poincare recurrence raise questions about infinity and probability that are so strange and so philosophically troubling that most physicists who have thought carefully about them wish they had not. Each of these will be explored in detail because each one illuminates a different aspect of what it means for the universe to have a finite existence, and because the specific mechanism of each ending reveals something different and important about the nature of the physical reality that surrounds you. The measurements being made right now by instruments including the Dark Energy Spectroscopic Instrument, currently the most precise three-dimensional map of the large-scale structure of the universe ever assembled, the Euclid Space Telescope launched by the European Space Agency, and future observatories including the Vera C. Rubin Observatory in Chile, are all aimed at the same fundamental question. What exactly is dark energy doing? Is it constant, growing, or diminishing? The answer written in those measurements is the death certificate of the universe. And we are, at this particular moment in the history of science, in the process of reading it. If these are the kinds of questions that reshape how you see everything you look at afterward, questions that sit at the intersection of the most precise experimental physics ever conducted and the oldest and deepest questions human thought has ever produced, then subscribing to this channel is the single most useful thing you can do right now. Every video here is built for exactly this. And what we are going to work through together over the remaining parts of this video is the complete picture of the universe's possible endings, laid out as honestly and as completely as the current science allows. The universe is dying. Let us find out, in every specific and unsparing detail, exactly how. The heat death of the universe is not a dramatic event. There is no explosion, no collapse, no final violence of any kind. It does not announce itself with a signal or a sound or a flash of light that crosses the cosmos to warn anything that might still exist of what is coming. It arrives the way sleep arrives in a person who has been awake too long, gradually, quietly, and without a precise moment you can point to as the boundary between one state and the other. The universe does not die in the heat death so much as it exhausts itself, spending down the last reserves of organized energy across timescales so extreme that the word long fails to carry any useful meaning, until there is simply nothing left that can do anything, anywhere, ever again. Understanding what that final state actually looks like requires following the physics forward through a sequence of eras, each one lasting longer than all the previous ones combined, each one representing a further stage in the irreversible dispersal of the energy that the Big Bang concentrated 13.8 billion years ago. What you find at the end of that sequence is not nothing. It is something far stranger and in many ways more unsettling than simple nothingness would be. We are currently living in what cosmologists call the stelliferous era, the age of stars. It began approximately 100 million years after the Big Bang, when the first generation of stars ignited from the primordial hydrogen and helium that Big Bang nucleosynthesis had produced, and it will continue for a very long time by any human measure of duration. The most frugal stellar furnaces, the dim red dwarf stars that constitute roughly 70% of all stars in the Milky Way and burn their hydrogen with such sparingly efficient that their lifespans extend into the trillions of years, will still be burning long after every star remotely resembling our Sun has exhausted its fuel, swelled, shed its outer layers, and collapsed into a cooling white dwarf. The last red dwarf stars are estimated to survive for somewhere between 10 and 15 trillion years, a span of time approximately 1,000 times longer than the current age of the universe. Every red dwarf that has ever ignited in the entire history of the cosmos is still burning today, because not a single one has yet had enough time to exhaust its hydrogen supply. They are the most patient furnaces in nature, and they will be the last light the universe ever knows from stellar fusion. When the final red dwarf exhausts its fuel and its core fusion ceases, there will be no new stars to replace it. The raw material for star formation, the vast clouds of hydrogen gas distributed through galactic disks, will have been either consumed into existing stars, ejected into intergalactic space through supernova explosions and stellar winds, or locked permanently into the remnants of dead stars in forms that cannot be reignited. The stelliferous era will be over. The universe will enter what physicists call the degenerate era, and the change it brings will be absolute. Every direction you could look from any location in the observable universe will reveal the same darkness. The galaxies that once glowed with billions of stellar furnaces will still exist as gravitationally bound structures, but they will be populated entirely by the cooling remnants of dead stars, white dwarfs slowly losing the residual heat of their formation, neutron stars radiating their rotational energy into the void, and the black holes that have been accumulating mass at galactic centers since the first billion years of cosmic history. No new light will be produced by nuclear fusion anywhere in the cosmos. The era of starlight, the era in which we exist and which has lasted from the first stars to the last, will be over. A white dwarf is one of the most remarkable objects in astrophysics. When a star like our Sun exhausts the hydrogen in its core, it expands into a red giant, fuses helium into carbon and oxygen in progressively hotter and denser shell reactions, and eventually expels its outer layers in a brief, beautiful planetary nebula phase, leaving behind a compressed remnant typically containing between 50 and 80% of the original star's mass, packed into a sphere approximately the size of Earth. This remnant is the white dwarf, supported against further gravitational collapse not by nuclear fusion, which has ceased, but by the quantum mechanical pressure of electrons resisting compression below a minimum volume dictated by the Pauli exclusion principle. White dwarfs produce no new energy. They do not burn. They are embers, radiating away the heat they accumulated during the star's active life, and they will continue doing so for as long as it takes to reach thermal equilibrium with the surrounding cosmos. How long is that? Current models suggest that a typical white dwarf will cool from its initial temperature of tens of thousands of degrees to something indistinguishable from the cosmic background on a timescale measured in quadrillions to quintillions of years. That is between 10 to the 15th and 10 to the 18th years, numbers so large that expressing them in years becomes almost meaningless. The universe's current age of 13.8 billion years is 10 to the 10th years. The cooling timescale of a single white dwarf exceeds that by a factor of roughly 100 million. We have not yet waited 1% of 1% of 1% of the time it takes for a white dwarf to go cold. During the degenerate era, the universe will also be losing mass at the quantum level through a process that was not known to exist until Stephen Hawking derived it theoretically in 1974. Black holes, which classical general relativity had described as perfectly stable objects from which nothing, not even light, could escape, are in fact slowly evaporating. Hawking showed that quantum mechanical effects near the event horizon of a black hole cause pairs of virtual particles to become real, with one particle escaping to infinity as thermal radiation and the other falling into the black hole, carrying negative energy that reduces the black hole's mass. The rate of this evaporation is inversely proportional to the square of the black hole's mass, meaning that smaller black holes evaporate faster and larger ones evaporate more slowly by an enormous margin. A stellar mass black hole, with a mass several times that of our Sun, would require approximately 10 to the 67th years to evaporate completely through Hawking radiation. The supermassive black hole at the center of the Milky Way, weighing approximately 4 million solar masses, would require roughly 10 to the 87th years. The largest known black holes, the ultramassive monsters lurking at the centers of the most massive elliptical galaxies with masses of tens of billions of solar masses, would take approximately 10 to the 100th years, a number physicists call a googol, to evaporate. These timescales are so extreme that everything else described in cosmology shrinks to insignificance beside them. By the time the largest black holes have evaporated, the protons that make up ordinary matter may themselves have decayed, a process predicted by certain extensions of the standard model of particle physics to occur on timescales of approximately 10 to the 34th to 10 to the 45th years depending on the specific theoretical framework considered. Proton decay has not been observed in any experiment, and its non-observation constrains but does not rule out most theoretical predictions for its timescale. If protons do decay, every atom in the universe that is not inside a black hole will dissolve, transforming the matter of cooling white dwarfs, neutron stars, rogue planets, interstellar dust grains, and any other material structures surviving into the late universe into a diffuse gas of electrons, positrons, neutrinos, and photons over timescales that are unimaginably long but still vastly shorter than the evaporation time of the largest black holes. By the time those black holes are gone, there will be nothing left but their evaporation products, a dilute bath of particles and photons expanding into an ever-growing void. What happens after the last black hole evaporates is what physicists mean when they use the phrase heat death. The universe at that point will contain an extraordinarily dilute collection of photons, neutrinos, electrons, positrons, and whatever particles the proton decay products and Hawking radiation have produced, all of them separated by distances growing constantly larger as the accelerating expansion of space continues to stretch the intervals between them. The temperature of this particle bath will be extraordinarily close to absolute zero, lower than any temperature that has ever been achieved in any laboratory on Earth, but not precisely zero, because the quantum properties of the remaining particles prevent a perfect equilibrium from being established in any finite time. The entropy of the universe will be maximized. No temperature gradient of any significance will exist anywhere. No concentration of energy sufficient to drive any physical process will be present at any location. No star will burn, no chemistry will occur, no information will be processed, and no structure of any kind will assemble. The universe will be in its final, permanent, irreversible state, and it will remain there, in an expanding darkness with nothing happening anywhere, for a duration that has no upper bound. This is heat death, not a violent event but a terminal condition, a state of maximum disorder that the universe approaches asymptotically, drawing closer with every passing moment since the Big Bang but never quite reaching it in any finite time, while remaining so close to it that for all practical physical purposes the distinction is meaningless. It is the ending that follows from the second law of thermodynamics applied honestly and completely to the largest closed system we know of. It is the universe's default fate, the destination entropy has been navigating toward from the first moment of creation. Everything that has ever existed, every moment of warmth, every star that has burned, every thought that has occurred anywhere in the cosmos, every structure that gravity has ever built, is being used up in the process of approaching this final equilibrium. Heat death is not waiting for the universe to run down. The running down is what we call cosmic history. But heat death is also the ending that requires the most time, and because dark energy does not appear to be perfectly constant, it is not necessarily the ending that the universe is actually moving toward. To understand the alternatives, you need to leave the comfortable realm of entropy and thermodynamics and enter territory that is in some ways even stranger, because the alternatives to heat death do not follow from the spread of disorder but from the dynamics of space itself, from the specific behavior of the dark energy that fills every cubic centimeter of the cosmos, and from what happens when the force driving the universe apart is not a gentle, persistent nudge but something that grows. Stronger and stronger and stronger without limit, until nothing in the physical universe can resist it any longer. Picture the observable universe as it exists right now. Galaxy clusters scattered across hundreds of millions of light-years, each one a gravitationally bound collection of hundreds or thousands of individual galaxies, surrounded by vast halos of dark matter and superheated intergalactic gas. All of it arranged along the filaments and walls of the cosmic web that emerged from the density fluctuations seeded in the first fractions of a second after the Big Bang. These clusters are separated by the cosmic voids, the enormous empty regions that dominate the volume of the universe, and the distances between them are growing as dark energy drives the accelerating expansion of space. But within each cluster, gravity holds sway. The mutual gravitational attraction of hundreds of billions of solar masses of matter is far stronger than dark energy's current ability to push things apart at those scales, and the clusters remain intact, their internal structure unchanged by the expansion happening between them. Zoom further into a single galaxy within one of those clusters, and the same principle applies. The Milky Way's gravitational coherence is not threatened by dark energy at its present measured value. Zoom further still into a single solar system and gravity's dominance is total. The Sun holds its planets in their orbits against the faint background pressure of dark energy as effortlessly as a planet holds a satellite in orbit against the irrelevant force of a distant feather falling somewhere on its surface. Now imagine that dark energy is not constant. Imagine that the energy density of the vacuum, rather than maintaining a fixed value as the universe expands, is instead growing. Slowly at first, imperceptibly at first, by amounts that no instrument could distinguish from constancy across a few billion years of observation, but growing nonetheless, compounding, accumulating, adding to itself with every increment of cosmic expansion, so that the force it exerts on space increases as the space it fills increases. In the cosmological constant model, dark energy dilutes as the universe expands, which sounds wrong until you realize that dark energy is a property of space itself, not a substance within space, so creating more space creates more dark energy in direct proportion, maintaining a constant density. In a phantom energy model, which is what this scenario represents, the density does not merely maintain itself but increases as space expands, meaning that every increment of growth makes dark energy stronger, which drives faster growth, which makes dark energy stronger still, in a feedback loop that accelerates without bound toward a singularity in finite time. Physicists who first worked through the mathematics of this scenario and followed the implications all the way to their conclusion gave it a name that is, for once in the technical vocabulary of cosmology, entirely appropriate. They called it the Big Rip. The Big Rip was given its modern mathematical treatment in 2003 by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg, who published a paper calculating the sequence of events that would unfold if dark energy behaved as phantom energy with a specific equation of state parameter denoted W, where the value of W determines how rapidly dark energy's density increases with expansion. In the cosmological constant model, W equals exactly -1. In quintessence models, W is greater than -1, meaning dark energy's influence weakens slightly relative to matter over time. In phantom energy models, W is less than -1, meaning dark energy's density grows with expansion. Current measurements of W from multiple independent surveys are consistent with -1 but do not rule out values modestly below it. The uncertainty in W is small enough to be scientifically meaningful but large enough to encompass the phantom regime. Whether W is precisely -1, slightly above it, or slightly below it determines whether the universe ends in heat death, something even stranger, or the Big Rip, and current measurements cannot yet distinguish between these cases with sufficient precision to be definitive. The answer is being measured. It has not yet been found. What Caldwell and colleagues showed was that if W is less than -1, the time until the Big Rip is determined by the specific value of W and the current measured expansion rate. For values of W only slightly below -1, the Big Rip could lie 20 billion years or more in the future. For values further into the phantom regime, it could be as near as 10 billion years from now. In either case, the sequence of events as the Big Rip approaches follows a specific and predictable schedule, because the timescale on which dark energy can overcome any gravitationally bound structure depends on the binding energy of that structure, which is a known quantity. The larger and more loosely bound the structure, the earlier dark energy disrupts it. The smaller and more tightly bound, the later. The first structures to be torn apart as the Big Rip approaches are the galaxy clusters, the largest gravitationally bound systems in the observable universe. Approximately 1 billion years before the Big Rip, the dark energy density will have grown to the point where its repulsive pressure exceeds the gravitational binding energy of typical galaxy clusters, and those clusters will begin to come apart. Galaxies that have been gravitational neighbors for billions of years will begin moving apart from one another. Not because their orbital velocities have changed, but because the space between them is expanding faster than gravity can pull them back together. The Virgo cluster, the nearest large cluster to our local group, will dissolve. The Perseus cluster, one of the most massive structures in the nearby universe, will dissolve. Every galaxy cluster within the observable universe will lose its cohesion within this billion-year window, their member galaxies dispersing into the expanding voids like seeds scattered by a wind that grows stronger with every passing moment. The galaxies themselves hold together longer, because the gravitational binding energy of a galaxy, with hundreds of billions of stars pulling on one another across tens of thousands of light-years of space, is much stronger than the binding energy of a loosely assembled galaxy cluster spread across millions of light-years. Individual galaxies like the Milky Way will survive for much longer after the clusters dissolve, perhaps until about 100 million years before the Big Rip. At that point, the dark energy density will have grown powerful enough to exceed the gravitational binding energy of galactic structures, and galaxies will begin to come apart as well. The stars will be scattered. The beautiful spiral arms of galaxies like ours, assembled over billions of years by the differential rotation of matter under gravity, will be pulled apart as the dark energy density grows beyond the binding energy of any gravitational structure spanning thousands of light-years. The stars will become isolated, each one drifting alone in an expanding space, no longer part of any galaxy, with the distances between them growing faster and faster as the rip accelerates toward its final moment. 3 months before the Big Rip, something remarkable and terrifying happens. The dark energy density will have grown to the point where it can overcome the gravitational binding energy of individual solar systems, and planetary orbits will destabilize. The planets of every solar system in the universe will be flung outward from their stars, not because anything struck them or because their orbits became dynamically unstable in the conventional gravitational sense, but because the expansion of space between a planet and its star will have become faster than the gravitational attraction between them can bridge. Earth, if anything recognizable as Earth still existed in a universe that has reached this stage, would be pushed away from the Sun in the final months before the Big Rip. The orbit of every planet around every star in every galaxy would widen and break within this 3-month window, sending trillions of worlds spinning away from their parent stars into a darkness that is, by this point, expanding so fast that the distances involved are growing to incomprehensible scales in fractions of a second. 30 minutes before the Big Rip, the stars themselves are torn apart. The gravitational binding energy of a star, the force that has held a sphere of plasma together under its own weight for billions of years, is overcome by the dark energy density at this stage, and stars across the universe will explosively decompress, their material expanding outward as the space it occupies grows faster than gravity can maintain coherence. This is not a supernova, not a detonation driven by nuclear processes, but a passive dissolution, plasma expanding because the space containing it is growing faster than gravity's reach. The scale of this event, happening simultaneously to every star in the observable universe within a 30-minute window, is difficult to characterize in any familiar terms. Every sun, every burning furnace, every source of light and heat that has sustained any chemistry, any surface temperature above the cosmic background, any possibility of life or complexity on any orbiting world, dissolving in the final half-hour of cosmic history. In the last fraction of a second before the Big Rip singularity, atoms themselves come apart. The electromagnetic force that holds electrons in orbit around nuclei, the strong nuclear force that binds protons and neutrons inside nuclei, and ultimately the forces that hold quarks together inside protons and neutrons, all of them are overcome in rapid succession by a dark energy density that has grown to infinity in finite time. Every atom in the universe dissolves. Every proton, every neutron, hydrogen, helium, carbon, oxygen, every element in every periodic table of every civilization that ever existed, if any did, comes apart as the quarks inside them are pushed apart by a force that has grown without limit from its current value through the compounding of phantom energy over the billions of years since the Big Bang. The universe ends not in coldness and darkness, but in a moment of total, simultaneous, absolute structural dissolution at every scale, from the largest galaxy cluster to the smallest subatomic particle, at a moment that physics can calculate and that arrives at a specific, finite time after the Big Bang, as determined by the value of the dark energy equation of state parameter W. What makes the Big Rip philosophically significant, distinct from heat death in its implications for how we should think about the universe, is not its violence but its finitude. Heat death, while inevitable, requires a duration that is effectively infinite from any practical standpoint, a future so long that no human concept of planning, no idea of legacy or memory or consequence, can meaningfully extend into it. The Big Rip, by contrast, could arrive in 20 billion years. In the context of the universe's current age, 20 billion years is not that different from the time that has already passed. The Sun has approximately 5 billion years of stable hydrogen burning remaining. Intelligent life on Earth has existed for something on the order of 300,000 years. If the Big Rip arrives in 20 billion years, that is 100 times longer than Earth has existed and 4 times longer than the Sun's remaining lifetime, but it is a specific, finite, utterly non-negotiable deadline for every structure in the observable universe. Not a tendency toward disorder. Not an asymptotic approach to equilibrium that never quite completes. A wall, a hard stop, a moment after which the concept of any physical structure, any particle, any force, any information ceases to have meaning, because the vacuum itself will have been torn to shreds. The Big Rip is not the universe winding down. It is the universe being unmade. And yet, as terrifying as the Big Rip is, it shares with heat death one important property. It is an ending that you can see coming, at least in principle. The dark energy density growing over time would leave signatures in the expansion history of the universe that surveys like DESI, Euclid, and the Rubin Observatory are specifically designed to detect. If the Big Rip is coming, physics should eventually be able to determine that it is coming with enough precision to put a date on it. There is something almost reassuring about that. The idea that even a catastrophe of this magnitude follows physical laws that can be understood, measured, and described. The scenario we turn to next shares none of that reassurance. It follows physical laws just as rigorously, and it too can in principle be studied and understood. But it cannot be predicted, cannot be detected in advance, and cannot, even in principle, be survived or escaped by anything anywhere in the universe. It is the ending that arrives at the speed of light from a direction you cannot know, carrying with it a different set of physical laws, and converting everything it touches into something that does not and cannot contain any version of you. The ground beneath your feet feels solid. The air you breathe feels real. The atoms that make up your body, the particles whose interactions constitute every sensation, every thought, every physical process you have ever experienced. All of them emerge from quantum fields that permeate all of space, and these fields exist in their current configurations because they are, as best as any measurement has ever been able to confirm, in their lowest available energy states. The stability of everything around you, the stability of the physical laws that govern the behavior of every particle and every force in the observable universe, rests on this assumption. Not as a guess, not as a hope, as the foundation upon which every atom in your body holds together. Every chemical bond in every living cell maintains its shape. Every star in the sky sustains its nuclear fire. If the fields that define the properties of particles and the strengths of forces are in their true ground states, their absolute lowest energy configurations from which no quantum fluctuation can permanently displace them, then the physical laws we observe are permanent features of reality that will remain unchanged for as long as the universe exists in any meaningful sense. The properties of the electron, the mass of the proton, the strength of electromagnetism, the range of the strong nuclear force, the specific parameters that allow atoms to form and persist and combine into the molecules that constitute chemistry and biology. All of these would be immutable features of a stable vacuum, reliable across every distance and every timescale in a universe built on a foundation that cannot collapse. These are not small things. They are the reason water is liquid at the temperature of a summer afternoon. They are the reason carbon forms the long-chain molecules that make biology possible. They are the reason you can read these words, think these thoughts, and exist as a coherent physical entity in a universe that seems, from where you are standing, reassuringly permanent. But what if the foundation is not as stable as it appears? What if the quantum fields that define the vacuum of space are not in their true lowest energy states, but are instead in a configuration that has remained stable throughout the entire 13.8 billion-year history of the observable universe, yet is in fact not a global energy minimum but a local one? A valley in the energy landscape of physics separated from a deeper valley by a quantum mechanical barrier. Think about what that means for a moment. The universe has existed for nearly 14 billion years. Stars have formed, burned, exploded, and seeded galaxies with heavy elements. Planets have cooled, oceans have formed, and life has evolved from single cells to organisms capable of asking questions about their own existence. And throughout all of that, through every stellar explosion, every planetary collision, every quantum event in every atom in every living thing, the vacuum has held. Not because it was required to hold, but because the barrier separating it from a lower energy state had not yet been crossed. In that case, the vacuum we inhabit would be what physicists call a false vacuum, a metastable state that is stable against small perturbations, but that could, given the right quantum fluctuation, spontaneously transition to the true vacuum, the deeper energy minimum, with consequences that would be immediate, total, and propagating outward from the point of the initial transition at the speed of light. It could initiate a bubble of completely different physics, expanding outward at the speed of light, carrying different laws, different forces, with no possibility of survival for any structure that existed in the false vacuum before the bubble arrived. Not survival in a diminished form, not survival in a different configuration, no survival at all. Every atom, every molecule, every structure built from the physics of the false vacuum. Gone instantly and completely, replaced by a region of space where the very rules that allowed those things to exist no longer apply. This is not a purely speculative possibility raised by theorists looking for extreme scenarios to consider. It is an active concern of the most precisely tested theory in the history of science. The Standard Model of particle physics, confirmed to extraordinary precision across decades of experiments at particle accelerators including the Large Hadron Collider at CERN, predicts the existence of the Higgs field, the quantum field that permeates all of space and gives mass to fundamental particles through their interactions with it. Without the Higgs field, electrons would have no mass. Protons would have no mass. Atoms could not form. Chemistry could not exist. The Higgs field is not a peripheral detail of physics. It is the mechanism by which the universe acquires the specific material properties that make structure of any kind possible. The Higgs boson, the particle associated with quantum fluctuations in the Higgs field, was discovered at the Large Hadron Collider in 2012 as one of the most celebrated scientific achievements of the 21st century, and as the completion of a theoretical prediction that had waited nearly half a century for experimental confirmation. When the announcement came, physicists around the world who had spent careers working toward that moment stood in lecture halls and wept. Not from sadness, from the recognition that the universe had finally revealed one of its deepest structural secrets, and that the revelation was real. The measured mass of the Higgs boson, approximately 125 gigaelectronvolts, carries with it, through the mathematics of the Standard Model, direct implications for the stability of the vacuum. Not indirect implications, not suggestions. Direct, calculable, unavoidable implications about whether the ground state of all of physics is truly stable or merely appears to be. When physicists calculate the shape of the Higgs field's energy potential, which determines whether the vacuum is stable, metastable, or unstable, they find that the measured mass of the Higgs boson places the universe directly in the metastable region of parameter space. Not comfortably stable, not clearly unstable. Exactly at the boundary between the two, within the measurement uncertainties of the current data. The universe is balanced on a knife edge between permanence and dissolution, and the knife edge is real. The calculation has been performed by multiple independent groups using different theoretical approaches, and the result is consistent and clear. Based on the measured mass of the Higgs boson and the measured mass of the top quark, which enters the calculation with great sensitivity, the Standard Model predicts a Higgs field potential with a second lower energy minimum at an enormous field value far above anything directly accessible to current experiments. There is a deeper valley in the energy landscape of physics. We are not in it. We are in a shallower valley that appears, from inside, to be the bottom. The vacuum we inhabit may be sitting in a higher energy local minimum, separated from this lower energy true minimum by a barrier that is large enough that spontaneous quantum tunneling from the false vacuum to the true vacuum is an extraordinarily rare event on any timescale accessible to human observation, but not so large that it cannot occur at all. The universe could be sitting, right now, in the same relationship to its true ground state as a ball sitting on a hilltop on an apparently flat surface, stable against small perturbations, but capable of rolling off catastrophically if the right fluctuation occurs. You would not know the ball was on a hilltop by looking at it from above. It would look perfectly still, perfectly safe, perfectly permanent, right up until the moment it was not. What would happen if vacuum decay began? The sequence of events that follows a successful quantum fluctuation into the true vacuum at some point in space is one of the most absolute and irreversible catastrophes that physics can describe. At the location of the initial tunneling event, a bubble of true vacuum would form, a tiny region of space in which the Higgs field has transitioned to its lower energy value and the physical laws governing particle masses and force strengths have instantaneously changed to their new values, determined by the parameters of the true vacuum rather than those of the false vacuum we currently inhabit. This bubble would be unimaginably small at the moment of its formation, perhaps smaller than a single atomic nucleus, perhaps smaller than anything we have the technology to detect or observe. But it would not stay small. The specific properties of the true vacuum are unknown, because we have never observed it, and the calculations that describe it depend on the precise shape of the Higgs potential at field values far beyond current experimental access. What is known from the general framework is that the true vacuum would have different masses for elementary particles, different coupling strengths for forces, and almost certainly different enough physical laws that the structures built from false vacuum physics, atoms, molecules, chemistry, biology, everything would be completely impossible within it. The true vacuum is not merely hostile to life. It is not a harsh environment where survival is difficult. It is not a region where things are hot or cold or pressurized beyond tolerance. It is a region where the specific physical laws that allow any of the structures we know about to exist simply do not apply. There is no version of you, no version of anything on the other side. The bubble of true vacuum would expand at the speed of light from the moment of its formation. Not approximately the speed of light, exactly the speed of light. The wall of the bubble, the interface between the false vacuum and the true vacuum, would travel outward in all directions at precisely the maximum velocity that relativity allows for the transmission of any information or influence. No rocket can outrun it. No signal can precede it. No warning can be sent ahead of it, because nothing travels faster than the thing you would need to warn people about. This is the property that makes vacuum decay uniquely terrifying among all the possible endings the universe could experience. Because the bubble expands at the speed of light, and because the speed of light is the fastest that any signal of any kind can travel, there is no physical mechanism by which any object, any civilization, any structure anywhere in the universe could receive advance warning of the bubble's approach. The first indication that the bubble was coming would be its arrival. And the interval between that first indication and the complete restructuring of every physical property of the local vacuum would be zero. Not a fraction of a second. Not a Planck time, the smallest interval of time that current physics has any reason to consider meaningful. Zero. The bubble wall would arrive and the physics would change instantaneously, in the same moment that any detector, any consciousness, any physical system sensitive to its environment would first become aware of it. There would be no last thought, no final observation, no moment of recognition. The awareness and the ending would be the same event. Inside the expanding bubble, nothing that existed in the false vacuum survives in any recognizable form. The Higgs field has changed its value, the masses of particles have changed, the strengths of forces have changed. Protons and electrons, if they can still be said to exist as distinct entities at all within the true vacuum, would have different masses and would interact via different force strengths. Atoms, if they could form at all, would have different sizes and different chemical properties. The specific coincidences of parameter values that allow hydrogen to form stable atoms, that allow carbon to have the nuclear resonances that make it the basis of organic chemistry, that allow water to be liquid at surface temperatures found on habitable planets. All of these depend on the precise values of physical constants in the false vacuum. Those constants are not universal truths. They are local facts about the specific vacuum we happen to inhabit. Change those constants, even modestly, and the entire edifice of chemistry built upon them becomes impossible. The periodic table loses its meaning. The molecular bonds that hold proteins together in living cells cannot form. The nuclear resonances that allow carbon to be synthesized inside stars in the first place, the resonances that Fred Hoyle predicted must exist because we exist, dissolve into configurations that produce no usable chemistry. The region of space consumed by the expanding true vacuum bubble would not be filled with some different form of matter and energy organized into different structures following different but internally coherent physical laws. It would be a complete annihilation of all physical organization at every scale, a region where the universe has settled into a lower energy state that may be more thermodynamically favored, but that is, from the perspective of anything that existed in the false vacuum, a place where the specific physical laws compatible with any complex structure of any kind simply do not exist. Not different life. not alien chemistry, not unfamiliar physics operating on familiar principles. Nothing that could be described, understood, or experienced by anything that came before. The bubble, once formed, expands forever. There is no mechanism within the true vacuum that would cause the bubble wall to slow or stop. Nothing outside the bubble can influence the expansion because the bubble wall travels at the speed of light, which is the fastest any influence can propagate. The bubble does not need fuel. It does not require energy to maintain its expansion. It is not a wave that dissipates with distance, not a force that weakens with the inverse square law. It is a phase transition in the vacuum itself, a change in the fundamental ground state of physics. And once that change has begun, it propagates outward through space as inevitably and as completely as a flame moving through dry paper, except that the flame is traveling at the speed of light and consuming not matter but the laws that govern matter. Over time, as the bubble grows, it would consume more and more of the observable universe, then more than the observable universe, then more than can ever be observed from any fixed vantage point. Sweeping through galaxy clusters, through intergalactic voids, through the cosmic web, through every structure in the cosmos, replacing the false vacuum and its physical laws with the true vacuum and its different physical laws everywhere it reaches without end, until either the entire universe has been converted or the universe's geometry prevents the bubble from reaching some regions. Given the flat geometry of the observable universe and the likely topology of what lies beyond the observable horizon, there is no strong reason to expect the bubble to be stopped before consuming everything accessible. The universe we know, the entire observable cosmos with its 2 trillion galaxies, its hundreds of billions of stars per galaxy, its planets and moons and nebulae and black holes, would be erased as completely as if it had never existed. Not destroyed in the conventional sense, converted, replaced, overwritten by a different set of physical laws that have no use for anything that came before. The probability that vacuum decay has occurred anywhere in the observable universe during its 13.8 billion year history is calculable in principle, though the calculation is sensitive to unknown parameters of the Higgs potential at high field values and to the effects of quantum gravity near the Planck scale that the current standard model does not incorporate. Published estimates using the best available parameters cluster around an estimated lifetime for the false vacuum of somewhere between 10 to the 100th and 10 to the 500th years, far exceeding the current age of the universe and the heat-death timescale alike. These numbers are so large that they effectively mean the same thing in practical terms. 10 to the 100th is a 1 followed by 100 zeros. 10 to the 500th is a 1 followed by 500 zeros. Both numbers make the current age of the universe, 13.8 billion years, or roughly 10 to the 10th years, look like nothing. Not a small fraction of nothing. Literally indistinguishable from zero when placed beside them. Machines that may or may not exist in any civilization's future. The vacuum may be safe for a duration that makes the heat death look brief. Or it may be on the verge of decaying right now, with a bubble already expanding toward us from some distant galaxy, carrying a wall of changed physics that travels at exactly the speed of light, arriving at this planet at a moment that the laws of physics permit to be any moment at all, including this one. If you find that last thought difficult to set aside completely, you are responding to it appropriately. Of all the ways the universe could end, vacuum decay is the only one that is both instantaneous and utterly unpredictable from inside the false vacuum. Every other ending gives the universe, in principle, time to exist through the process that leads to its termination. Heat death plays out over durations that make every human concept of time feel like nothing, but it plays out, takes time. There is a sequence of events. Stars age and die. Black holes evaporate. Matter decays, entropy accumulates, and through all of it, the universe exists, changes, evolves, before reaching its final state. The Big Rip gives warning through the physics of an accelerating expansion that measurements can detect. The distances between galaxy clusters begin to grow unexpectedly. Then the galaxies themselves come apart. Then solar systems destabilize. Then stars dissolve. The end comes violently and completely, but it announces itself in the language of physics to any civilization sophisticated enough to read the measurements. Even the Big Crunch, the opposite scenario in which gravity eventually reverses the expansion and collapses everything back into a final singularity, would be visible as a deceleration in the expansion rate long before its completion. Any civilization observant enough to monitor the cosmic expansion would see the deceleration coming. They would have time, vast amounts of time, measured in billions of years, to know what was happening and, if nothing else, to understand it. Vacuum decay gives nothing. No warning, no signal, no deceleration in the expansion rate, no change in any observable quantity in the sky. No precursor event of any kind that any instrument could detect. No physical mechanism by which any structure in the false vacuum could become aware of the approaching bubble before the bubble wall arrives and converts the local physics into something incompatible with the existence of that structure. It is the ending that could be happening right now, somewhere in the universe, silently at the speed of light, without any announcement and without any possibility of response. And if it is happening right now, somewhere in the universe, you will never know. Nothing will ever know. The knowledge and the end will be the same moment. Everything discussed so far, heat death, the Big Rip, vacuum decay, represents the universe's future under conditions where dark energy maintains its current dominance over the expansion. But physics does not require dark energy to behave this way forever. The measurement of dark energy's equation of state, the parameter that tells cosmologists whether dark energy's density is constant, growing, or diminishing as the universe expands, carries measurement uncertainties that currently encompass not just the cosmological constant value and the phantom energy regime, but also values of W greater than -1, meaning dark energy could be weakening over time rather than holding steady or growing. If dark energy is a dynamic field whose energy density is slowly diminishing, the history of the universe's expansion could eventually reverse. The accelerating expansion of today could decelerate, stop, and give way to a contraction. And if that contraction proceeds without interruption, the universe could end not in the cold dispersal of the heat death or the violent instantaneous tearing of the Big Rip, but in the mirror image of the Big Bang. A final compression of all matter and energy back into a state of infinite density and temperature that physicists call the Big Crunch. The Big Crunch was, for most of the 20th century, considered the most likely alternative to eternal expansion. For decades, it was the second option on the cosmic menu. Either the universe expanded forever, slowing gradually under the influence of gravity but never quite stopping, cooling toward a final darkness over incomprehensible timescales. Or gravity won. The expansion slowed, halted, and reversed. The universe contracted back toward a final singularity that mirrored the one from which it had emerged. Before the discovery of dark energy in 1998, cosmologists understood the universe's fate as determined by a single question. Did the universe contain enough matter to gravitationally halt and reverse the expansion? Or was the expansion fast enough to escape gravitational collapse permanently? The parameter measuring this was the density parameter omega, the ratio of the actual matter density to the critical density required for a spatially flat universe. If omega exceeded 1, gravity would win and the universe would eventually recollapse. If omega was less than or equal to 1, the universe would expand forever, decelerating but never stopping. The discovery of dark energy revealed that this framing had been incomplete, that the relevant question was not only about matter density, but about the combined contribution of matter, and dark energy to the overall energy budget of a dynamically complex system. Dark energy, with its negative pressure contributing to accelerated expansion, changed the calculation entirely. It did not merely add a new variable. It overthrew the entire framework through which cosmologists had been thinking about the universe's fate. In the current best-fit cosmological model, the universe will not recollapse on any timescale accessible to current physics. Dark energy is winning, decisively, for now. But the current best fit model depends on measurements that, while precise by any historical standard, still carry uncertainties. The DESI survey's first-year results, released in 2024, produced significant attention when preliminary analyses suggested hints that dark energy might be evolving over cosmic time in ways that slightly prefer dynamic models over the cosmological constant. These hints are not confirmation. They are not proof. They are the kind of tentative signal that appears at the edge of current measurement precision and requires more data to interpret with confidence. But they are real, and they are taken seriously by the cosmological community precisely because the question they touch, whether dark energy is constant or evolving, is the most important question in cosmology. If those hints represent genuine physical signal rather than statistical noise or systematic measurement error, and further data collection will eventually clarify this, they could indicate that dark energy is weakening. Whether weakening dark energy would lead to a big crunch depends on the specific trajectory of that weakening, which of the many possible dynamic dark energy models describes the actual behavior, and how the competition between a diminishing dark energy and the matter density of the universe plays out over potentially enormous timescales. Some models in which dark energy weakens do lead to eventual recollapse. Others do not. The current data can distinguish neither the direction of dark energy's evolution with sufficient precision, nor the specific model well enough to draw conclusions about whether a big crunch is in the universe's future. The question is open. The measurements are ongoing, and the answer, when it comes, will be written in the light of distant galaxies observed by instruments that some of us alive today helped to build. What would the big crunch actually look like if it occurred? Running the physics forward from a scenario where dark energy diminishes to the point where gravity regains control of the expansion, the initial observable consequences would be a gradual deceleration of the cosmic expansion, measurable in the redshifts of distant galaxies showing less recession than expected for a continuing accelerating expansion, until at some future epoch the expansion halted entirely and the universe began, slowly at first, to contract. The transition would not be dramatic. For billions of years after the expansion stopped, the universe would look almost the same as it does today from the inside. Galaxies would still be separated by enormous distances. Stars would still be burning. The night sky on any inhabited world would still show the same general darkness punctuated by distant points of light. The contraction would begin at the largest scales, the distances between galaxy clusters beginning to diminish rather than grow, while the internal structures of those clusters remained gravitationally organized and essentially unchanged. Galaxies would gradually move closer together. The cosmic web would begin to invert its character, voids compressing as the filaments and clusters were pulled inward by the gravity of a contracting cosmos. For any observer watching on a timescale of billions of years, the universe would look like a film of the current epoch played slowly in reverse. The structures that took billions of years to form would take billions of years to unmake. Eventually, galaxy clusters would begin to merge. Then galaxies themselves would collide with increasing frequency as the average distance between them decreased. The night sky from any world in the contracting universe would grow progressively brighter as more galaxies entered the observable horizon, and the aggregate light from the universe's entire stellar population converged rather than dispersed. The darkness between the stars would slowly fill with light. Not the harsh light of proximity, not yet, but a growing, gentle luminescence spreading across the sky from every direction. The collective glow of 2 trillion galaxies drawing slowly, inexorably together. As the contraction continued, the temperature of the cosmic background radiation would increase, because the photons of the CMB that have been cooling as the universe expanded would be blue-shifted rather than red-shifted by the contraction, their wavelengths shortened rather than lengthened by the shrinking space they were traveling through. The universe would begin to warm, not locally, everywhere. At some point before the final singularity, the background temperature would have risen to the point where it exceeded the surface temperature of stars, and stellar radiation would no longer cool the surfaces of those stars into space, because the surrounding radiation field would be hotter than the stellar surface. Stars would be heated from outside rather than cooled by radiation into the void. The physics of stellar interiors, the delicate balance between nuclear energy generation and radiative cooling that keeps a star in equilibrium for billions of years, would be disrupted by an external thermal bath that stars were never designed to inhabit. Stars would not simply stop shining. They would begin to dissolve into the rising temperature of the cosmos around them, their boundaries blurring as the distinction between stellar interior and cosmic exterior collapsed. As the contraction continued further, the background temperature would exceed the temperature of stellar interiors, and the distinctions between stars, gas, and the radiation field would dissolve as everything was compressed into a single increasingly hot and dense plasma, reversing in compressed form the entire sequence of cosmic history from the Big Bang to the present. The universe would be running its story backward. Not exactly. The structures would be different, the galaxies would be differently arranged, the chemical composition of the cosmos would reflect nearly 14 billion years of stellar nucleosynthesis. But thermodynamically, energetically, the universe would be approaching the conditions that existed in its first moments, approaching them not as a memory but as a physical reality, a state of heat and density that the laws of physics were driving it toward with the same inexorability with which they had driven the expansion for all the billions of years before. The universe would approach its final singularity in a state that mirrored the conditions of its earliest moments, a growing plasma of radiation and matter at increasing temperature and density, until the current limits of physical theory were reached and the physics of the singularity itself, which general relativity cannot describe from within, took over. And then silence, or something we cannot describe, because no theory we have can speak from inside a singularity. Whether the Big Crunch is truly an ending depends on whether it is followed by a new Big Bang. This question, which is not answerable from within the Big Crunch itself, any more than the nature of the Big Bang is knowable from within the singularity that preceded it, has motivated a number of theoretical frameworks that propose the universe's history is not linear but cyclic. The universe, in these frameworks, does not have a beginning and an end. It has a rhythm, a cosmic heartbeat, expanding, contracting, expanding again, with each cycle beginning where the last one ended and ending where the next one begins. The simplest and most direct cyclic proposal is the ekpyrotic model developed by Paul Steinhardt and Neil Turok in the early 2000s, in which our universe is a three-dimensional membrane or brain embedded in a higher dimensional space, separated from another such brain by a tiny gap. The Big Bang, in this framework, was not a true beginning of everything but a collision between the two brains, an event that released enormous energy into our universe and initiated the expansion and cooling that led to the cosmos we observe. The brains drifted apart after the collision, carrying the energy of the impact with them. The universe we inhabit is the aftermath of that collision, the expanding, cooling, structure-forming epoch that followed the bang. In the future, the two brains will drift together again, collide again, and produce a new Big Bang, beginning another cycle of expansion, cooling, structure formation, and eventual collapse. The ekpyrotic scenario makes specific predictions about the pattern of temperature fluctuations in the cosmic microwave background that differ subtly from the predictions of standard cosmic inflation, and future CMB experiments may be able to distinguish between the two frameworks. If they can, and if the data favors the ekpyrotic prediction, it would constitute evidence not merely for a different model of the Big Bang but for the existence of extra dimensions and the cyclic nature of cosmic history. Roger Penrose, whose contributions to theoretical physics span 6 decades and include fundamental work on the geometry of spacetime, black holes, and the nature of singularities, has proposed an alternative cyclic cosmology called conformal cyclic cosmology, which takes an entirely different approach to the transition between cosmic cycles. Penrose does not invoke extra dimensions or colliding brains. His framework arises from a single, elegant observation about what happens to a universe that has reached the heat death. In Penrose's framework, the heat death of the universe is not a dead end but a beginning. In the very far future, after all black holes have evaporated through Hawking radiation, All massive particles have decayed or otherwise lost their rest mass, and the only remaining content of the universe is massless radiation. Penrose argues that the universe loses track of scale. Massless particles, which travel at the speed of light, do not experience the passage of time, and without time, scale becomes meaningless. A universe of only massless radiation cannot distinguish between being enormously large and extremely small, because the concept of size requires a reference standard involving massive objects that can serve as clocks. Without clocks, there is no time. Without time, there is no distance in any meaningful physical sense. And without distance, the question of whether the universe is unimaginably vast or unimaginably small dissolves into a mathematical equivalence. In this scale-free state, Penrose proposes the remote future of one universe is geometrically equivalent to the Big Bang of the next. The heat death is the Big Bang. The ending is the beginning. The vast, cold, empty universe of the far future is, in the appropriate mathematical sense, the same as the hot, dense, energetic universe of the very first moments. And from that mathematical equivalence, a new universe emerges. The universe cycles through an infinite succession of eons, each one beginning with a hot, dense singularity and ending in a cold, dark expansion, and the transition between eons leaves faint imprints in the cosmic microwave background that Penrose and his collaborators have claimed to detect in existing CMB data, though the significance and interpretation of those claimed signals remains actively debated. Whether those signals are real is a question that more precise CMB measurements will eventually answer. Both cyclic models share a feature that sharply distinguishes them from the terminal scenarios considered earlier. They offer the possibility that the universe does not end in any final sense, but rather transforms, with the matter and energy of the current universe becoming the substrate from which a new universe emerges. Whether this constitutes consolation depends on whether you believe continuity of physical content across a singularity preserves anything that matters. The new universe in any cyclic scenario would not remember the previous one, would not contain any information about what existed before, and would not in any physical sense be a continuation of the universe that preceded it. Whatever existed in the universe before the transition, whatever civilizations, whatever minds, whatever structures, would be gone as completely as if they had never been, their information permanently erased by the singularity or the transition, regardless of whether a new universe emerged on the other side. The cycling continues, but nothing within any individual cycle carries over. Each universe is born, lives its full cosmological lifespan, and ends completely, and the next universe has no knowledge of and no connection to anything that came before. There is no reincarnation here. No cosmic memory, no thread of continuity running through the succession of eons. Only the physics, the same equations expressed through new initial conditions, playing out their consequences again from the beginning, in ignorance of all that came before. The question of proton decay also deserves attention independently of the larger scale scenarios, because it represents an ending for ordinary matter on timescales that could precede even the heat death by many orders of magnitude. Protons are the positively charged particles that, combined with neutrons, form the nuclei of every atom in every substance in the universe. Every atom of oxygen in the air you are breathing right now contains protons. Every atom of carbon in your body, every iron atom in your blood, every calcium atom in your bones. All of them built on the foundation of protons whose stability or instability determines how long ordinary matter can exist. In the current standard model of particle physics, protons are stable. They do not decay. A proton in isolation, far from any other matter and under no external influence, is predicted by the standard model to remain a proton indefinitely, with no tendency towards spontaneous transformation into lighter particles. This stability is related to the conservation of baryon number, a quantum number that counts the total amount of proton-like matter in a system, which the standard model predicts to be conserved absolutely. In the standard model, protons cannot decay because the total amount of baryon number in the universe cannot change. But the standard model is not a complete theory. and most of the theoretical frameworks propose to extend it, including supersymmetric theories, grand unified theories that attempt to combine the strong and electroweak forces into a single unified force at high energies, and string theory-inspired models predict that baryon number is not absolutely conserved but is violated at some level corresponding to proton decay with a specific lifetime. In these theories, protons are not immortal. They simply live for an extraordinarily long time. The predictions for proton lifetime in these extended theories range widely, from approximately 10 to the 32nd years in the most minimal grand unified theories to 10 to the 45th years or longer in more complex frameworks, with significant uncertainty even within any given theoretical approach. Experiments designed to observe proton decay, most notably the Super Kamiokande detector in Japan, a 50,000-ton tank of ultrapure water surrounded by light-sensitive detectors and located deep underground to shield it from cosmic ray background, have not yet observed a single proton decay event, despite monitoring an enormous number of protons for decades. Super Kamiokande contains roughly 10 to the 33rd protons. Each one has been watched patiently year after year for signs of decay. Not one has yet obliged. The non-observation has ruled out the simplest minimal grand unified theories, which predicted lifetimes shorter than current experimental limits, but has not ruled out the broader class of models predicting longer lifetimes. Proton decay may happen. We have simply not yet waited long enough to see it. And given that the predicted lifetimes exceed the current age of the universe by factors of billions or trillions, the waiting will be long. If protons do decay on timescales of 10 to the 34th to 10 to the 45th years, the implications for the far future are profound and specific. Every atom of ordinary matter in the universe that is not inside a black hole or in some exotic stable state will eventually dissolve, its protons transforming into lighter particles, typically a positron and a neutral pion that quickly decays into photons, releasing a tiny burst of energy and leaving behind no stable matter. Stars would not need to exhaust their nuclear fuel in this scenario, because their protons would decay on timescales shorter than their fuel-limited lifetimes for the most rapid decay models. The stars would not burn out. They would quietly dissolve. A sun like ours, not expanding into a red giant, not collapsing into a white dwarf, simply losing its protons, one by one, each one transforming into a flash of radiation too faint to detect individually, until the mass of the star had drained away like water from a cracked vessel. Planets would erode into nothing over immense but finite timescales. The rocks beneath your feet, the iron core of the Earth, the oceans, the atmosphere, all of it built from atoms whose protons are slowly, imperceptibly, counting down toward their individual expiration dates. Every gram of rock, every drop of water, every atom of carbon in any structure anywhere in the universe would eventually dissolve into radiation and leptons through proton decay, leaving behind a universe in which the concept of ordinary matter has simply ceased to exist, long before the black holes have finished evaporating and the heat death has fully arrived. A universe without matter, without atoms, without chemistry, without anything capable of storing or processing information. A universe that has become, through the slow silent decay of its own substance, a place where nothing we recognize as physical reality can exist. Among the larger scale scenarios, two of the most unusual and philosophically disturbing possibilities also deserve mention: Boltzmann brains and Poincaré recurrence. These do not represent an active ending for the universe, but rather raise questions about infinity and probability so strange that most physicists who have thought carefully about them wish they had not. They are the kinds of ideas that seem almost too strange to take seriously, until you follow the logic and realize that if certain basic assumptions about physics and infinity are correct, these possibilities are not merely conceivable but mathematically inevitable. Ludwig Boltzmann was the 19th century physicist who established the statistical foundations of thermodynamics and defined entropy through probability theory. His insight that the second law of thermodynamics emerges from statistics rather than from any fundamental directional principle was one of the deepest contributions to physics of the 19th century. It was also, eventually, the source of one of the strangest thought experiments in the history of science. An extraordinarily unsettling possibility that emerges from Boltzmann's framework. If the universe truly exists forever, and if random quantum or thermal fluctuations can eventually produce any configuration that is statistically possible, then over sufficiently long periods, long enough that even times after the heat death are included, random fluctuations could produce a fully functional thinking entity that exists instantaneously, complete with false memories consistent with a past and beliefs about its surroundings, complete with a lifetime of experiences that feel entirely real, complete with the sensation of reading these words, in this moment, believing itself to be a physical being with a continuous history. This speculative entity is called a Boltzmann brain, and its existence raises deep philosophical problems about the reliability of the observations we use to test cosmological theories. If Boltzmann brains can be produced in astronomical numbers, it may be statistically more likely that a random observer is such a brain rather than a genuine being with a real evolutionary history, an implication that undermines the reliability of our observations and constitutes one of the deepest epistemic paradoxes in current physics. How do you know you are not a Boltzmann brain? You cannot know. Your memories of a continuous past, your sense of embodiment in a physical world, your conviction that the observations you are making right now correspond to a real universe, all of these would feel identical whether you were a genuine evolved observer or a spontaneous quantum fluctuation that appeared a fraction of a second ago with all of those experiences already in place. This is not a problem most physicists spend time worrying about in their daily lives, but it is a problem that sits quietly and persistently at the logical foundation of any cosmology that posits an infinite future. Poincare recurrence is a similarly disturbing but different concern. The mathematical theorem proved by Henri Poincare states that any state of a system with finite phase space will, given sufficient time, return to a state arbitrarily close to its initial state. Not exactly the same, but close enough to be physically indistinguishable. If the universe's phase space is finite or at least has an accountable structure, this means the universe could eventually return to conditions very close to those of the Big Bang's initial state. Not exactly, but potentially indistinguishably close after an extraordinarily large but finite amount of time. The galaxies, reassembled from their dispersed constituent particles by the improbable but not impossible convergence of quantum fluctuations. The stars, reignited from the debris. Planets, reformed. Life, re-evolved. Not the same life, not the same history, but a configuration so close to the original that no physical measurement could distinguish it from the return of what came before. The required waiting time would be on the order of 10 to the 10 to the 100th years or larger, a number meaningless by any conceivable standard of comprehension. A number so large that writing it out in full would require more digits than there are atoms in the observable universe, and each of those digits would itself require more space to write than the entire observable universe contains. But if the universe truly exists for that long and Poincare recurrence applies, it means everything could begin again, not just once, but an infinite number of times. Every configuration that has ever existed, every person, every civilization, every thought, recurring again and again across a time span that has no end. Whether this is a consolation or an additional source of dread depends largely on one's personal perspective. Whether the recurrence is truly a return or merely a physical coincidence with no connection to what came before is a question that physics cannot currently answer. Bring everything together now, because the final chapter of this story is not really about physics at all. The physics has been laid out. The mechanisms have been described. The timescales have been given, from the relatively near 20 billion years of a possible Big Rip to the effectively infinite duration of the heat death's approach, with vacuum decay lurking as an undated wildcard that could arrive at any moment without warning. Each scenario follows from a different answer to the question of what dark energy is doing and will do, and current measurements cannot yet definitively choose between them. The science is active, the instruments are collecting data, the analysis pipelines are running, and within the coming decade or two, Measurements precise enough to narrow the possibilities significantly will be available. We may not yet know exactly how the universe ends, but we know the options, we know the physics behind each one, and we know that the answer is not a matter of interpretation but a fact about the physical world that exists independently of whether any mind has ever wondered about it. The universe will end in a specific way for a specific physical reason, and the process that leads to that ending is already underway, governed by laws that do not make exceptions. It was underway before any human being existed to observe it. It will continue after the last human being is gone. It is not waiting for our understanding. It is not sensitive to our preferences. It is simply physics unfolding on its own terms at its own pace toward its own conclusion. But what does it mean that the universe ends? This is the question that physics cannot answer on its own. The question that remains after all the numbers have been calculated and all the mechanisms have been described. It is the question that physics hands off to us, as though the equations themselves, having delivered their verdict, step back and say, "We have told you what will happen. What you make of it is your own." Throughout the history of science, we have grown accustomed to discovering that the universe does not care about us. Copernicus showed that the Earth is not the center of the solar system. Hubble showed that the Milky Way is not the center of the universe. The cosmic microwave background showed that the universe has no center at all in any privileged sense, that every location is equivalent to every other from the perspective of the large-scale structure of space. Each of these discoveries required an adjustment in how we understand our relationship to the cosmos, a recognition that the universe does not organize itself around our presence or our preferences, that its structure and its history were determined by physical processes that preceded us by billions of years and that will continue after us by trillions more, indifferent to whether we are here to observe them. Each of these discoveries, when first announced, felt disorienting, potentially threatening, as though something had been taken away, and then gradually something else took its place. Not consolation exactly, but a different kind of wonder, a recognition that the cosmos we inhabit is vaster and stranger and more indifferent than we had imagined, and that this vastness and strangeness and indifference does not diminish us. It locates us. It shows us where we actually stand. The discovery that the universe ends adds a new dimension to this picture that has no precedent in the earlier revolutions of scientific understanding. The earlier discoveries required us to accept that we are not at the center of things. This one requires us to accept that there is no permanent thing to be at the center of. The universe itself, the totality of space and time and matter and energy and physical law, the framework within which all existence and all experience occur, is a temporary structure. Not temporary in the sense of being likely to end soon. Not temporary in the human sense at all, because the timescales involved make the entire history of life on Earth, the entire history of human civilization, the entire span of any future that civilization might plausibly have, look like an infinitesimal fraction of the available time. But temporary in the physical sense. Bounded, finite, mortal. The universe has an end date, even if we do not know the date precisely, even if that date lies so far in the future that no concept of duration we normally employ can reach it. The universe will end. That statement is, as best as current physics can determine, simply true. What follows from this truth is not despair, and it is not the kind of existential vertigo that the phrase "the universe will end" might initially suggest when encountered without preparation. It is something more interesting and more difficult to characterize. Something that requires holding two thoughts in mind simultaneously and allowing them to sit there together without resolving the tension between them too quickly. The first thought is this: nothing you care about, nothing that has ever been built or created or discovered or loved by anything anywhere in the observable universe, is permanent. Not the sun, not the earth, not the atoms that compose any structure you have ever touched. Not even the physics that allows any of these things to exist. Everything is temporary. The laws that govern today's universe, the the specific values of physical constants that allow hydrogen to form atoms and carbon to form organic molecules and liquid water to exist at surface temperatures found on habitable planets. These are not eternal features of reality, but contingent facts about the particular configuration of quantum fields that happens to describe the vacuum we inhabit. They were not inevitable. They emerged from a specific set of initial conditions that did not have to be what they were. They will not last forever. They represent one possibility among many, realized in this universe at this epoch, for reasons that physics can describe but cannot call necessary. Everything that exists, including the laws that govern existence, is borrowed. The second thought, which needs to be held simultaneously with the first, is this: none of this diminishes what exists right now by a single measurable amount. The fact that the sun will eventually exhaust its fuel and swell into a red giant does not make its light less warm on a clear afternoon. The fact that every atom of carbon in every living thing will eventually decay through proton decay or be consumed in the heat death does not make the chemistry of any living cell less intricate or less extraordinary. The fact that the observable universe will eventually be reduced to a collection of isolated gravitational islands separated by an expanding void, each one slowly cooling toward a state where nothing happens anywhere, does not retroactively remove from existence the 10 billion years of stellar burning and planetary cooling and biological complexity that preceded that ending. What happened, happened. The Big Bang was real. The first stars ignited in the real universe. Every supernova that scattered heavy elements through the interstellar medium of a real galaxy made a real contribution to the chemistry of every world that later formed from that enriched gas. Every thought that has ever occurred in any mind in this universe was a real event in the physical world, governed by real physical processes, constituting real information. None of it is erased by the knowledge that the physical system containing it will eventually reach an end state. The past is the one thing the universe cannot undo. What has already happened is permanent in a way that nothing in the future will ever be. The heat death cannot reach backward through time and unmake what the universe has already been. The physicist Richard Feynman, in one of his recorded lectures, described the feeling of knowing that things do not last as one of the most productive realizations a scientist can have. Not because it resolves anything or provides comfort, but because it focuses attention on what is actually present rather than on some imagined permanence that was never really there. The universe we are studying, the one whose ending we have been tracing through its multiple possible scenarios, is the universe that actually exists, and its existence is an extraordinary fact regardless of its finite duration. That it exists at all, that a set of physical laws compatible with structures as complex as galaxies and stars and planets and living organisms and minds capable of wondering about the ending of everything should have resulted from a quantum singularity 13.8 billion years ago, is not made less remarkable by the knowledge that those physical laws are contingent, and that the vacuum supporting them is either metastable or destined to be consumed by entropy or ripped apart by phantom energy or collapsed in a final big crunch. The contingency does not diminish the fact. If anything, it deepens it. The universe did not have to be this way. It is this way. And this way, it turns out, permits stars and oceans and living things and minds that can stand at the edge of all they know and look outward into the dark and ask questions that the dark does not answer. There is also something specific about this moment in cosmic history that deserves attention. Something noted in passing earlier, but that becomes more significant when considered in the context of all the endings described here. We are living at a time when the observable universe is still accessible in its large-scale structure, when the cosmic web of filaments and voids is visible in all its three-dimensional complexity, when the cosmic microwave background still carries detailed information about the universe's earliest moments, when enough galaxies are still within our event horizon that we can map the expansion history of the cosmos across billions of years of look-back time, and when the measurements being made by our instruments are actually capable of distinguishing between different models of dark energy and therefore between different possible endings for the universe. This is not a permanent situation. The window is open now. It will not always be open. In a future dominated by dark energy in even its mildest, most cosmological constant-like form, the observable universe will steadily shrink as more galaxies recede beyond the event horizon. The accessible evidence for the universe's origin and large-scale structure will diminish, and the ability to determine from observation alone what kind of universe this is and what kind of ending it faces will gradually disappear. The universe is becoming less knowable with every passing moment. Not because we are losing intelligence or instrumentation, but because the evidence is receding, because the light from the most distant galaxies is being carried beyond the horizon faster than it can reach us, because the universe is in the process of hiding its own history from any mind that might someday try to read it. A civilization existing 100 billion years from now, if any did exist, would inhabit a cosmological desert. The 2 trillion galaxies visible in today's observable universe would have been reduced to a handful of local remnants. The cosmic microwave background would have cooled and stretched beyond any detector's reach. The expansion history written in the distribution of galaxies across billions of light-years of observable space would be inaccessible, because there would be no galaxies to observe at those distances. The dark energy that is determining the universe's fate would still be present and still operating, but the evidence from which its equation of state could be determined would no longer exist in any accessible form. That future civilization, if it existed, would look up at a nearly empty sky and know nothing of what we know. It would have no way to discover that the universe began with a Big Bang. It would have no way to measure the expansion rate and deduce the presence of dark energy. It would have no access to the cosmic microwave background, the single most informative signal the universe has ever produced. That future civilization would be cosmologically blind in a way that we are not, unable to determine from within its observable universe whether the cosmos had a Big Bang origin, whether there were once 2 trillion galaxies beyond its horizon, or what physical mechanism was driving the darkness that surrounded its isolated gravitational island on every side. All of the information we are currently gathering and all of the measurements currently being made about the nature of dark energy and the fate of the universe exist within a specific window of cosmic time during which that information is available. We happen to exist within that window, not by design, not because the universe arranged things for our benefit, but because the physics of cosmic evolution produces a brief interval near the beginning of the stelliferous era when the evidence for origins is still accessible, and we exist during that interval. This is the thought that deserves to stay with you after the physics has been absorbed. Not fear of the Big Rip, though the physics of it is genuinely staggering. Not dread of vacuum decay, though the impossibility of warning or preparation that it implies is as close to pure existential exposure as any physical scenario can come. Not even the quiet horror of the heat death, the universe spending down its last organized energy across timescales so extreme that human language buckles under the effort to express them. What deserves to stay with you is the recognition that the universe is knowable, that the same physical laws that guarantee its ending also allow, for a brief interval of cosmic time, structures complex enough to investigate those laws, to determine the universe's history from the faint afterglow of its creation, and to calculate, with quantitative precision and genuine confidence, the range of ways that everything that exists will eventually cease to exist. The universe is not merely dying. It is dying in a way that can be understood by part of itself for a limited time, before the information required for that understanding disperses beyond recovery into an expanding void. There is something extraordinary in that, something that does not fit comfortably into any category of feeling. Not hope, not despair, not awe in the conventional sense, but something that partakes of all three and reduces to none. The universe, through the improbable emergence of minds capable of physics, has briefly become aware of its own ending. And it is aware of it now. Through you. You are that part. Right now, in this specific moment of cosmic history, which will not return, and which did not exist for the overwhelming majority of the universe's past, and will not exist again for any part of its future, The universe is understanding its own ending through every mind that has followed this story to its conclusion. That is not nothing. It is, in fact, the most extraordinary thing that the physics of a dying universe has ever produced. Not the galaxies, not the stars, not the intricate chemistry of life, but the capacity, present briefly in the history of a cosmos destined for dissolution, to look at all of this clearly, to follow the physics wherever it leads without flinching, and to understand what it means. The stars will go out. The last black holes will evaporate. The vacuum may decay. The heat death will arrive, or the big rip will tear everything apart, or the big crunch will collapse everything back into the fire that started it all. One of these will happen. We do not yet know which, but we know that one of them is real, that the answer is written in the behavior of dark energy, and that the measurements being made right now are slowly, patiently reading that answer from the light of distant galaxies. The universe will end in physics, in hard, irreversible physics, as certainly as it began. But it will have been here. All of it. Every star, every galaxy, every moment of complexity assembled by gravity and nuclear fire and chemistry and time from the wreckage of the Big Bang. And for a brief, extraordinary interval near the beginning of its story, it will have been understood. Look up tonight. The light reaching your eyes left those stars years and centuries and millennia ago. The universe that sent it is already different from the universe that will receive what you send back. Everything is moving. Everything is changing. Everything is eventually ending. But the ending has not arrived. The stars are still burning. The physics is still running. And the most consequential question in all of science, the question that determines which ending is coming and when, is being answered right now by instruments and minds that exist for this exact and fleeting purpose in the only universe that has ever produced anything capable of asking it.